Okay, so welcome. Today's lesson is on, well, Dr. Wagner or Wayne. Today's lecture is on the momentum equation, part 2. We're going to work some example problems. The objective of today's lecture is to apply linear momentum in combination with Bernoulli and continuity to solve problems. So basically, we've developed the momentum equation, and now we want to see how to use it. As everything, that's kind of the most difficult part. So right here I have written out a common kind of use of the momentum equation. I have written it as the sum of forces equals basically the sum of the momentum flux going into a control volume equals, the sum of the momentum leaving the control volume. And then I've got this term on the end here, which is the delta, the change in momentum, mass times velocity divided by time. One of the things that we want to be clear about here is that these little arrows on top of the F, on top of so like right there, and right there, and right there. So little arrows mean that these are vector quantities, and we need to remember that at all times. Okay, so so this is actually as many equations as you have dimensions in your problem. So this could be a three-dimensional, if you have a 3D problem, which isn't going to really happen very often in kind of undergraduate fluid mechanics, but you could end up with this equation in X, this equation in Y, and this equation in Z. More often than not, you're going to end up with 2 dimensions or even 1 dimensions. I'm going to start with the 1D, and we'll kind of see how to use those arrows. Okay. The other thing to note is that these M's have dots on them. Okay, so just be aware that that's the mass flux rate. So typically M dot is rho Q. Okay, so that's kind of pretty standard. And so you'll see that as I kind of go through, I'm just going to kind of assume that that's something that we can do. Okay, so let's get into the problems, and we're going to work 3 of them today. One of them will be a linear momentum problem, or I guess they're all linear momentum, but one of them will be just flow through a contraction as shown here. And then the next one will be flow in a bend. Excuse me for that. And we're going to take this equation and we're going to bring it with us. We're not going to take that with us. And so here's what we've got. We've got water flowing through a nozzle as attached to the end of a laboratory sink faucet. Oh, geez. Had a little trouble with that. Okay. So water flowing through a nozzle shown attached to the end of a laboratory sink faucet. I think that hopefully most of you guys have seen these laboratory sink faucets. I mean, I always remember them from lab class or whatever. And I remember that you could turn the nozzle and the water would just come out like, really, really, really fast. In this case, the flow rate it doesn't seem like it's terribly high, 0.6 of a liter per second. I don't know if that's a lot or a little. I guess if you think about a liter bottle and you thought that that's coming out, you're basically filling up half of that in a second. That's pretty quick. Anyway, if the mass of the nozzle, so that's the mass of the metal that makes up the nozzle itself, is 0.1 kilograms, and the mass of the water in the nozzle, so the water in the nozzle, we could draw that like, that's all this stuff right here. Okay, that has a mass of 3 times 10 to the negative 3 kilograms. Okay, so there's really not really that much water in there. What is the force required to anchor the nozzle in place? Okay, and so if you're wondering, where does that force take place? That force is taking place kind of like, right in these, in the teeth of this, of the screwing mechanism. Okay, so basically, and I think you can imagine it. If this thing were not screwed on, you turn that thing on, this nozzle is going to fly and it's going to hit the bottom of the sink. Okay, and so our expectation basically is that at the end of the day, our force is going to be upwards. Okay, our force anchor, we're expecting to be upwards. And so that's usually the way I like to do my problems, where I always assume a positive direction just because it makes things a little easier. But it would be very surprising, and in fact, if you were to get a downward answer, I think you should probably be worried. Okay, so let's go ahead and let's get rid of all that. And let's start here with the flow rate, okay? And I want to start with the flow rate before I get into the tools even, because this is an unusual unit. We don't like this unit. Maybe you're a sort of person who likes this kind of units. I don't really like this unit, so I'm not really going to want to work with this unit. So the first thing I'm going to do is I'm going to convert liters per second into something a little bit easier. Okay, so we're going to convert that. Ooh. Okay, this is going to be, okay, so we've got Q equals 0.6 liters per second. Okay, this is not a very precise instrument I have here. Okay, I'm going to multiply it by 1 cubic meter per 10 to the thirds liters. Okay, and we're going to get a Q that is a little bit more reasonable. Okay, so we're going to say that Q now equals 6.0 times 10 to the minus fourth cubic meters per second. Okay, so so that's just to get everything kind of easier. Okay, so I'm just going to write that over here and kind of get it out of the way. Q equals 6.0 times 10 to the negative fourth cubic meters per second. Okay, so that means I can erase all this and kind of keep my diagram in good order. Okay, so now we've got these tools, and I want to think about these tools, and I put them in I wouldn't say a random order because that wouldn't be useful, but this is the order probably, well, son of a, okay, I guess it is kind of a random order. Okay, so it's a bit of a random order, and the key here is right now we know, because this is the lecture on momentum equation, that we're going to use momentum, and that's probably going to be the point of this problem, because that's this lecture. But that's cheating. What happens when this pops up on a test or something along those lines, right? So how do we know which one we want to use? And so one of the things is that I recommend when you're looking at these tools is that, or I can kind of give you rules for each one. So momentum, anytime you need forces on a moving fluid, you're going to need momentum, because that's the only one that's going to deal with fluids, with forces on moving fluids. Okay, this is a fluid that's moving through this nozzle, and we're calculating an anchoring force, which means we need momentum. So the momentum equation is essentially going to be our master. Okay, so I'm going to put in parentheses right here that this is our master. Okay, all these others are going to inform the momentum equation, and so we're going to work with that. So the first thing I'm going to do is I'm going to take this momentum equation here, and we only have one dimension. So I'm going to deal with these little arrows right now. So the dimension that we have is the z direction. Now, some of you may prefer y. However, in this, I always prefer z. But in this problem, it's actually defined for us. Okay, whoever wrote this problem told us beforehand that this was going to be in the z direction. Okay, so this equation then becomes sum of forces. So we've got a problem here, which is, if we're going to sum forces, we have to think in terms of a free body diagram. Okay, and there's a few different ways to do this. I'm going to do this kind of the harder way first. It's not really that much harder, but it's just going to kind of nail it down. And so what I'm going to do is a free body diagram of the control volume of the water. Okay, and so this is key. We are drawing a free body diagram of the water. Okay, and the water has a shape like this. Okay, and obviously it's not perfect, it's not beautiful, but it is what it is. So now we have to think about it. We have to think about what forces do we have on this. So always when dealing with momentum equation, and when you're thinking about the forces, so we've got body forces. Oh, don't do that, please. Okay, body forces, which is basically weight. And then we've got surface forces. Okay, so that's basically every time something is touching the surface of the water. Okay, so basically these four lines that I drew to kind of estimate the edges, I need one of those edges. So what do we have there? Well, we've got the kind of the friction or the viscosity. Okay, so that's one type of force. We've got normal forces. Okay, and then we've got pressures. Okay. Okay, so the normal forces are taking place on these walls. This is where a normal force would take. The pressures are going to be where there's another fluid resting against it. And the viscosities are going to kind of be acting along these walls in that direction. Now you're thinking, okay, well, this is an awful lot of force. Oh, and then of course we've got the weight, and the weight's going to be coming down. And so you're thinking, oh my Lord, this is an awful lot of forces. How are we going to handle all this? Okay, and I'm going to take this one at a time. Don't worry, we're going to write them all in here. So the first thing we've got is we've got the weight, right? Okay, weight. And the weight for us is actually fairly straightforward because it told us the mass of the water. So if you know the mass of the water, you multiply times gravity, you get the weight. Okay, so now we're going to go down here. We've got viscosities and normal forces, and then we've got the pressure. So I'm going to deal with the pressure right now. The pressure right here, okay, it looks like this. Okay, and it's spread over that surface of water, or the top of that free body diagram of water. And so this force is going to be P, we call that section 1, P1A1. Okay? And now on the bottom down here, okay, we've got another one pushing back up, which should be P2A2. However, in this case, it's releasing into the atmosphere, and we're assuming that P1 up here is going to be given to us in gauge. Okay, and I think that's always a fair assumption. So if that is given to us in gauge, then this one down here at section 2 can be taken to be 0. Okay, so this is the atmospheric pressure. So we're going to go ahead and delete that one, okay, because we don't want to deal with it. Okay, get out of here. Okay, now these other forces, the viscosity and the normal force, okay, these are forces that come from the wall, or I guess it's kind of, the walls of the nozzle. And together, they kind of add up and they give us what we're looking for, which is that anchoring force, okay? Because all of these is how much, well, it's not really the anchoring force, but it's basically what I'm going to call, I'm going to draw it right in the middle, although really it's happening at the walls. And I'm going to call this the force, I'm going to call it nozzle on water, force now, okay, nozzle on water. And you'll see that I do that a lot. This helps me to clarify whether I'm solving for the force of the nozzle on water or if I'm solving for the force of water on nozzle, force 1. And in this case, we're working on force nozzle on water, okay? And that, and so we're gonna go with that, and then we'll talk about how to deal with that later. Okay, so these are our forces. So that tells us how to open up this term right here, our force term. Okay, this term right here. Okay, so then we've got our out term. Okay, and maybe I'll change colors for these. Let's do that color. Okay, so this is a velocity, okay? And it's a velocity in. So this velocity is right here, okay? And that's going to be V1. Okay, and so that is a momentum flux. Basically, that flow is carrying momentum into this control volume. Okay? Similarly, V2 is down here, okay, and that's V2. V2 is carrying momentum out of the control volume. So those two combined are having an effect, depending on which one of those is stronger. I mean, this is, of course, is how rocket engines and that sort of thing work. So, so that's good. But what's nice about this is those are the only two velocities. We've got one in and one out. So we've got one term here, and we've got one term here. Okay, now this last term is, in some ways, we should be thankful for this, but in this class, we're almost never going to deal with something that is accelerating, that is gaining momentum in time. This, of course, happens. Fluids do gain momentum in time, but generally speaking, this class is not going to happen. And in this case, there's nothing to imply that the flow rate or the momentum inside this control volume is increasing. Anyway, I've also kind of discretized this equation. Normally you see this written as a derivative, and this equation can get much more complicated. We're just really not going to use it very much. So we're going to use it like this. Okay, so what I'm going to do now is I'm going to erase all my marks on this thing. How do I do that? Eraser. There you go. And give me a nice fat eraser. Okay, and let's just go ahead and go back to the color coding. And we're going to color code our forces, okay? So in the vertical, it looks like we've got 3 forces. Okay, the one I'm looking for, F, N, O, W. Okay, that one's up. I just assumed a direction, okay? And then I'm pretty sure that the nozzle is pushing on the water upwards. It's possible it's going the other way, but I'm pretty sure. Okay, but regardless, we're just going to assume a direction. Okay, now we're going to subtract P1, A1. Okay, and now we're going to subtract the weight. Okay, so those are my forces. Okay, in the Z direction. Okay, notice I'm no longer worried about arrows because I've accounted for that. I've made this all forces in the Z direction. Okay, next. Okay, let's do the mass, this term right here. Okay, in. Okay, so now I need to add, okay, this particular velocity, and this is kind of interesting, it's a negative velocity. So this mass flux, okay, the mass flux is easy, okay, so that's going to be rho times Q, okay, so that's m dot. And then this V, okay, it's got an arrow on it, so that means that we have to take account of that negative sign, negative V1. Okay. Now we're going to do the equal sign, equals, equals. Okay, now we'll do this term right here. Okay, and that's V2, okay, because that's where it's exiting. So again, we'll do m dot, which is rho Q. These are always easier when there's just one in, one out, because the m dot is the same. And then this thing, also notice the V has an arrow on it. So this is also going to be negative V2. Okay, and now this last term, of course, as we mentioned earlier, this thing goes away. We're not going to worry about that. Okay. So now we have to figure out how to solve this. And so I call this the master equation. I kind of wish I'd give myself more space on it, but we'll figure it out. Okay, so this is our master equation. So what I'm going to do is I'm going to go through here with the green, and I'm just going to kind of talk about what we know and what we don't know. Okay, F now, that's what we're looking for. Okay, so this is our big question mark. Okay, P1, A1 is given. P1 is given right here. And A1, where we're given the diameter. So this is all known. So I'll give you little check marks. Okay, the weight. Well, the weight is the mass times the gravity, the mass of the water times the gravity, so we're good there. Okay, rho, well, it's water, so that's given. Okay, so we can know it both of those places. Q, Q is given, we solved for it over here. Okay, this is Q right here. Okay, so Q is known, both places. And then V1 and V2. Now V1 and V2, we don't know, right? They gave us Q and they gave us some areas, but we don't know V1 or V2. So what we're going to do here is we're going to look up at our tools up here, okay, these guys, and we're going to decide which ones of these are going to help. So this is unknown, right here and right here. Okay, so that's what we want to look for. So what we're going to do is we're going to go up to our tools. Continuity could help with this. Okay, I don't think Bernoulli is going to be any help. Okay, if you think back to Bernoulli, P1 on gamma plus Z1 plus V1 squared on 2G equals a constant. Okay, I could pick 2 points. I know the Z's because this is given right here. So I would know Z1 and Z2. I know pressure 1 and pressure 2 because pressure 1 is given and pressure 2 is at the atmosphere, so that would be a 0. But then the V's, we would have two V's in this equation, so we couldn't solve for them this way. Okay, so what we need to do instead is we need to use, well, let's see, geometry. The geometry is clearly not going to give us the velocities, so we'll scratch that out. We'll scratch Bernoulli out. And then hydrostatics, there's nothing static in this whole equation, this whole drawing, so we can't use that. So we have to use continuity. So let's go ahead and let's use continuity, and I'll go back to kind of the standard color here. I don't know why this thing doesn't have black. Oh, because I'm working in black, of course. Why doesn't it have white? Anyway, okay. So, all right, so let's go ahead and solve for these V's. I'm going to go ahead and undo all this scribbling. You know what? I don't want to undo all the, well, let's undo all the scribble. Wish I could just go back to a certain point. Okay, let's see. Okay, so that's our equation. So now let's do continuity. So continuity, the way we typically work with that is we're going to say in equals out plus accumulation. Okay. this one's nice and easy, right? Because in, so that's m dot in, so that's going to be rho q in. So that's rho at position 1, q at position 1, equals out rho at position 2, q at position 2. And then, you know, nothing's accumulating inside this thing. This water is the same now as it was, as it ever will be. So this accumulation goes away because there's, you know, it's neither gaining nor losing mass in there. Okay, so now we note that since it's incompressible, that means rho 1 equals rho 2, which means we can get rid of those. Okay, which means Q1 equals Q2. Okay, we only have one Q, and that's 6.0 times 10 to the negative 4 from over here. I'm going to have to figure out how to do this a little better. Let's try moving that over. Okay, so, all right, so that means that Q, okay, either 1 or 2, or we could say Q1 or Q equals V1 A1, okay, and so we can solve for that, and that's where we'll get our V1. So we'll say 6.0 times 10 to the negative 4th meters cubed per second equals V1, whereas, V1 is what we're solving for, V1 times the area pi times diameter 1, which appears to be 16 millimeters. So careful with those silly units. Divided by 4. Okay, if we solve that, V1 equals, hold on, I got this, 2.9842 meters per second. Okay, note that I always keep 5 significant digits throughout the problem, and then I'll report 3 at the end. Okay. So now we are left with solving for V2, which we will use the exact same method, obviously with a different diameter, 6.0 times 10 to the negative 4th meters, cubic meters per second equals V2. I guess technically these should be W's, but we'll just use V's. V2, area pi, 0.005 meters squared over 4. Note that your expectation here is that the velocity is going to go a lot faster here because it's a much narrower opening. And when we pull it into the calculator, that is in fact what we get. Okay. So now I've got these two numbers. Okay. I've got this number. Oh no, it's moving everything. Let's undo. I was hoping I could just get that thing. Huh. Okay. So yeah, so we've got these velocities now. Okay. So now we're ready to plug everything back into our equation up here. So I wonder if there's a way. I wonder if I could just like. Nope. Undo that. Let's do this. Well, sure. Why not? It's a little janky. Okay, so now I think we're ready to solve. Okay. So we just need to start plugging in. So we've got F now. Let's get a writing tool. Okay, so F, nozzle on water, minus P1A1. Okay, so that's that was 464 kPa, newtons per meter squared. Okay, times area 1, which is going to be pi. We probably could have solved for the area earlier, just so we don't have to keep writing all this out. Okay, minus the weight of the water, so that's the mass of the water, 3.0. Oh no, it's just 3. Let's get that eraser. Times 10 to the negative 3rd kilograms times gravity, 9.81 meters per second squared. Okay, plus, oh wait, okay, so those are those terms. Now we'll go to red. Plus rho, the rho of water. Hopefully you've got this nailed down now. 1,000 kilograms per cubic meter. okay, times Q, which we decided was 6.0 times 10 to the negative fourths cubic meters per second. Okay, negative V1, okay, that negative sign is important, 9842 meters per second equals, okay, and let's keep scrolling up. Okay, and these momentum terms always kind of look the same, which is nice. 6.0 times 10 to the negative fourths cubic meters per second. And then this is going to be a negative V2, which is 30.558 meters per second. Okay, so at this point, what we're going to do is we're going to go ahead and check our units. Okay, notice this guy should be measured in newtons. We've got newtons here, got a meter squared here and a meter squared here, so this is going to be newtons. We've got kilograms, meters per second squared. That is the definition of a newton. So this one works, this one works. Over here, we've got cubic meters, kilogram, okay, so those go away. We've got kilograms, seconds, okay, so I got kilograms, meters, seconds squared. Okay, so again, that's the definition of a newton, so we're good. Okay, so let's get rid of all that mess. Okay, so let's go ahead and let's go ahead and solve this. I'm going to put in one intermediate step here just so that we can see what's going on. Okay, so we can kind of get an idea of the magnitude of these forces, 92.293 newtons. Okay, so that's the force of pressure inside the nozzle, minus the weight of the water, 0.029430 newtons. Okay, very small. Okay, minus 1.7905 newtons. Okay, so notice that the, okay, well, I'll finish it, but okay, equals negative 18.3335 newtons. So I think this is kind of interesting. The first things to note before we kind of move on too far, notice that the pressure is the dominant force in this case. Obviously, I could have altered the pressure number to make it not dominant. Of course, at some point, if I altered it too much, the Bernoulli equation is not going to work. We could probably plug this back in to see if Bernoulli does work. I'm assuming that whoever came up with this problem, that this is the correct pressure that would make this problem work. Notice the weight of the water is very small. I think that's kind of expected. The other things to note is that the water that's coming into our control volume right here, okay, is pushing it downwards. And I think that makes sense. Most of us can kind of imagine that. But then this one has the opposite sign. I mean, it has the same sign, but it's on the other side of the equation, but it has the opposite effect. So when the water exits, its net effect is to help hold the nozzle up. And notice it's a lot stronger than the one going in. Okay, so that's just kind of like a little intuition, something to think about. So if we solve this, we get F nozzle on water equals, okay, and the number for this is 76.778 newtons. Okay, and note that this number right here, this includes the viscosity and the normal forces, okay, between the walls of the nozzle and the water. Okay, but unfortunately, this is not what the problem was asking. The problem was asking about the nozzle. Okay, it wanted to know about the anchoring forces on the nozzle, and this is how hard the water is pushing on the nozzle. So what we're going to do here, let's undo that. What we're going to do here is, oh wow, this is getting really spread out. So let's not do that. Let's undo that. Okay, so let's go over here. And so I'm going to draw another free body diagram. Okay, so this will be another free body diagram. Let me zoom in a little bit. Okay, this will be a free body diagram. Okay, it doesn't like it though if I do it like that. Okay, this will be another free body diagram. This is of the nozzle. Okay, and so if we're going to do the nozzle, then the nozzle's got a kind of an interesting look, right? I'm not going to be great at drawing it, but it looks, actually, yeah, it does kind of look like that, doesn't it? Okay, that's the nozzle, more or less. Okay, now it's got, now we want to think about the forces on it, because what we're going to do is we're going to say that this nozzle is not moving, right? And so the first thing to be aware of is this. Okay, this is the force of the nozzle on the water. This means that the force of the water on nozzle is going to be negative 76.778 newtons, or force water on nozzle equals 76.778 newtons downwards. Okay. So I'm going to go over here and I'm going to say the force of the water on the nozzle, I'm going to draw it downwards like that. Okay. And I'm just going to say that that's 76.778 newtons. Okay. The other way to do it is I could have drawn it upwards and noted that its value is negative 76.778, but I don't feel like doing that. Okay. So now we've also got the weight of the nozzle, okay, going downwards. And then the only reason this thing is not flying off the, off onto the thing is that there is an anchoring force. Okay. And that anchoring force is taking place inside these, I don't know why my brain's not working today to come up with a name for that. Okay. So this is an easy equation, at least. There's not a lot of terms, and we should be able to solve them. Okay, force of the anchor minus the weight of the nozzle, so that's the mass of the nozzle times gravity, okay, minus 76.778 newtons. And that's the water pushing on the nozzle. Okay, so if we do the math here, we'll go ahead and plug all that in. F anchor minus the mass of the nozzle, which from the givens was very small, 3. Yep, that is ugly. Okay, 3. Did I get a different thing? I did get a different thing. Okay, 3 times 10 to the minus 4. Wait, is that right? No, 0.1. Sorry, my apologies. For some reason I can't delete that thing. Okay, I can delete it. Just gotta be careful. Okay, 0.1 kilograms times 9.81 meters per second squared minus 76.778 newtons equals 0. And the, let's see, where are you? F anchor equals 77.8 newtons. Okay, notice it's upward as we expected. Okay, so that's kind of the gist of how we do these problems. It looks a little bit disorganized now, and I like how I got much bigger over here. Okay, it's not because it's more important, that's just how it happened. Okay, hopefully that made some sense. What I'm going to do at this point is, let's see, I'm going to get rid of some of this stuff because it's in my way. And I'm going to take this equation and I'm going to bring it over to the next problem because I want to use it over here. Okay, so we're going to go, well, we're going to, you know what, you go away. You can shrink. You go over here. You all can be a mess. I hope I never want to use this again. All right, so we're going to solve a second problem. And so this one, okay, we know we're using momentum equation because I've got it written there. Okay, and what should kind of pop out at you is, look, we're going to definitely be in 2D this time. Okay, and I've got my tools over here written out again, and we've just kind of got an interesting problem here. So let me move my notes around a little bit, and let's see what happens. Okay, so this one will probably be more involved than the last one because we've got 2 dimensions. A lot of times in problems on tests or quizzes or things like that, people will ask you to solve for one of the directions just because it saves time. What I'm going to do here is I'm going to give myself more space than I did last time, and I'm going to spread the momentum equation out to the right, and I'm going to do all the asides down here. So we're going to do the asides over here. Oh, get out of here. Okay, so over here, Let me give myself some space. Okay, now. Okay, so let's do this. Okay, so first we know that we're working with the momentum equation. So that's what's going to come out here. So let's talk about the problem a little bit. Okay, so we got, I already did all this. Okay, we've got the water, and it's coming in at point 1. It's coming in this way, and it's exiting this way. Okay, we know the diameters of the pipe at 1. We know the diameter of the pipe at 2. Okay, we know this angle alpha, and we know how much flow is coming in here. Okay, note this is a very auspicious number. It seems a little contrived, if you ask me. Okay, we know that so this pipe, notice that this symbol usually means the pipe continues, and then we're just looking at a section of the pipe. Okay, so that means this is pressurized. So at P1, it's 21 psi. At P2, it's not atmospheric because this pipe continues. We don't know what the pressure is. Okay, which is kind of interesting. The mass of the bend, so that's the mass of the pipe that creates this thing. So it's all of this stuff out here. Okay, so whatever that pipe is made out of is 1,000 slugs, which is insane. Okay, but that's because I made that number up. Okay, you know, why not? Okay, and then the volume of the water in this thing is 10 cubic feet. Okay, so it's the volume of the water in the bend. Okay, and then Z2 equals Z1. You know, I really should be zoomed in while I'm doing this. Okay, and then Z2 equals Z1 plus 2. So this spot right here is 2 feet higher than that spot here. Sometimes in a lot of problems they'll say just neglect that 2 feet. We'll see on this one. They'll just say, you know, like if you were given this problem and someone didn't give you this dimension, I think most of the time it would be safe to just kind of like draw a little star and assume that Z2 minus Z1 equals 0, because that's just going to be a little bit easier. We'll work through this and see if this 2 feet ends up mattering. It may. We'll see. Okay, I don't really remember. I think I made that number up too. I think this one initially did not have that. Okay, so let's start by, what I'm going to do is I'm going to ignore all this for a second. So we're going to ignore all this. Okay, not for any good reason, really for bad reasons, or not really for bad reasons, but it's because I know that we are going to be over here, and I know that that this is going to be my master equation. And again, I mean, I don't think I said this last time, but what I mean by the master is this is the one that's going to give us our answers. Okay, and what we're asking for here is the force of the water on the bend, so we're looking for a force of a moving fluid. So we're going to have to use momentum equation. There's really just no way around that. So I know I'm going to need this equation, and unfortunately, I think it should be fairly clear that this problem is going to have an x and a y component. So I'm going to do the x component right here. Okay. Well, let's not get ahead of ourselves. Let's draw the free body diagram first. Okay, so that's going to help. Okay, so here we go. Free body diagram. It looks like this. Okay, not the world's best free body diagram, but it'll work. Okay, so now that we've done that, let's do some forces. Okay, so what forces do we have on this? On this fluid. Okay, remember this is the free body diagram. Oh no, none of that. This is the free body diagram of the water. Okay, so remember this is the free body diagram of the water. Okay, or of the control volume of the water. Okay, so we need to think about the forces, okay? And so if we start with the body forces. Well, there's only one body force, and it's always there, right? Weight. The only way that we wouldn't have to account for weight would be if the problem were only in the horizontal plane, which is not what's going on here, okay? This thing can move upwards, okay? Unfortunately, it says Z1 and Z2, although it gives us the dimension as Y. That's a little weird. Just think of those as vertical. Okay. Anyway, so what else do we need here? Okay, so now we've got weight. Okay, so now what other forces do we have? Well, we've got a force of the bend on the water, right? And so somewhere in here, there's a force of the bend on the water, force, and I always like to call this the force Flux. And then they gave us this as the y coordinate, so we'll call this force Bowie. BOWY. Okay, now some part of you at this point is going to be wondering, let's just get rid of this line. Let me grab it, delete it, it's annoying. Okay, get out of here. Okay, so some point in time, if we stare at this, okay, so we are missing some forces here, okay? And this is a little bit more interesting than the last one in that regard, and that we have forgotten about pressure, okay? These pipes are not open to the atmosphere. So this right here is P2A2. And then on this end, we've got a pressure here. Now notice pressure is always pushing. It will always push, P1A1. Okay, it's always going to push, no matter what. There's no way around that, okay? So don't, I mean, people always ask this question. They always want to know, it's always pushing. It's pushing, this part of the pipe is pushing on that part, and that part's pushing back. So that's what it means to be pressurized. Okay, so and that's the only thing pressure can do is to push. Okay, so now we're going to do these velocities, and we want to note that the velocities, okay, because those are all the forces. So we've got 5 forces, which is a lot of forces. Okay, and now we've got these velocities, and I'm going to draw them in red. So this one is V1 coming in, and here's V2 leaving. Okay, so it's kind of a lot. It's pretty messy. Okay, but let's see what we can do with that. Okay, so let's do my X momentum X. Okay, so we're going to start with the sum of forces. We're going to keep that in blue. Okay, so these are going to be X forces. So, well, the big one, the one we're looking for is F. I don't know if it's big, but it's important because we can't solve the problem if we don't get it. F Baux. Okay, F bend on water in the X direction. Okay, again, we think we probably have the wrong sign on that one, but that's okay. And then we're going to, let's see, we're going to add P1A1. Okay, we also have the other pressure term. Let's undo that. Let's do the pressure terms in green, plus P1A1 minus, we've got the other pressure term, P2A2, but it's on an angle, right? So we're going to need, let's see if I can put that angle in there in such a way that alpha. Okay, we need it such that alpha is 30 or 45. I can't remember for this problem because we went to the other page. But we know it's going to be the cosine of that alpha, so it's not terribly important. Okay, so all the forces kind of split out. The green ones are the pressure terms, so those kind of go into there too. Okay, so those are all the X forces. Yeah, 3 X forces. Okay, so now we're going to say equals. And now we're going to get the Y forces, or not the Y forces, I forgot. Okay, it doesn't equal. We're going to add the in term, okay? So now we are using red. Okay, so now we've got this V1 term. Okay, and so we've got an M dot, which is going to be rho. This is annoying. So we've got a rho Q. Okay, rho 1, Q1. We'll put 1s on there for now, but note that they're the same for 1 as they are 2, so it's gonna be, it's gonna be fine. It's gonna cancel out. And then we've got V1, which I'm gonna put in parentheses, positive V1. And remember, I put that positive there just because I want to remind myself that I took care of the sign. Okay, and then for equals, it's going to equal the other half of this equation. Okay, which is going to be, okay, so that was this guy. And then we need what's leaving. Oh, stop that. Okay, so that's going to be rho 2, Q2, and then this is going in the positive X direction, plus V2, but it's at an angle. So we're going to make it plus V2 cosine alpha. Okay, and that's our equation. That's what we're looking for. Okay, and that's a lot. Okay, and that's not the only equation. We've got 2 of these. Okay, so I'm going to set up another one, but this one, of course, is going to be in the Y direction or the Z direction. In this case, it's defined as being the y direction. So y direction, let's give myself a little bit more space. Eraser, just give me an eraser. Okay, so we're gonna go down here, y. I'm gonna have F Bowie. Okay, so that's the force in the y direction. We've now got a weight that we have to deal with. Okay, now we're gonna go ahead and get the green color. Okay, note that the P1A1 does not act in the y direction, so we won't use that. We will use P2A2. It is acting in negative P2A2 sine alpha. Okay, so there's 3 forces in the x direction, 3 in the y, I think, unless I've missed one. Okay, so we've got 3 in the x direction, 3 in the y. PA1A1 acts only in the x direction. P2A2 acts in both. W only acts in the y direction. And then we've got the force Bowie and Bow x. Okay, so now we need to do our momentum fluxes. So go ahead and add, and then we'll switch to green. Okay, and notice that V1, not green, we want red. Okay, notice that V1 does not happen in the x direction. Okay, so this is a big fat 0. Okay, because V1 doesn't happen in the y direction. Okay, so then the y direction, however, this V2 does happen in that direction. So we need m dot, rho 2, and Q2. And then it's going in a positive y direction, but we only have part of it, sine alpha. Okay? And as always, for both of these, I didn't worry about this term right here because we're just not going to worry about that in this class. Okay, the key right now is that you understand how we got that. Okay, that's the fundamental point of this lecture is, can you get that? Once you get that, the rest of this is doing things that hopefully we've already learned. Okay, so for example, if we go here, this is what we're looking for, this is what we're looking for. Okay, P1. Is P1 given? I think P1 is given. P1 is given, yes. A1, we have all the areas. Okay, P2, well, okay, we can get the weight of the water. Okay, P2 is unknown. Okay, that's something we're gonna have to get at. Okay, so that's gonna keep us from solving either of these. Okay, the angle, we know the angle, so we're good there. We obviously know the value of 0. We know rho because it's water. We know Q because it's given. V1 and V2 are going to require some more help, but we know rho 2 and rho 1 because it's the same everywhere. Okay, so this is what we're after. We're after P2 and we're after our velocities. Okay, and that's where we're going to go and look at these tools. Okay, and that's how we're going to figure out what we need. Okay, so I'm going to get rid of all that because it's muddying up the works. But what we're going to remember is that we're looking for P2 and we're looking for V1 and V2. Okay, and then once we get those, we can come back to this. This is our master equation, and we can solve the whole thing. Okay, so let's go back over here and let's solve for these things. Okay, and so we need to figure out which equations we want to use. Okay, I'm going to work from the top down. Well, I don't know what I'm going to do. Okay, let's just start with continuity and see if that will be useful for us. Okay, so if we know that Q, okay, so in equals out plus accumulation. Okay, in this case, there is no accumulation because that pipe is solid. Okay, N is rho 1 Q1 equals rho 2 Q2. Okay, the rows are the same, so I can say Q1 equals Q2. This looks like what we just did a second ago for the other problem. And so I can say V1A1, well, let's just cut to the chase here. Let's get back to the chase here. What is the chase? Okay, the chase is Q equals V1A1, okay, and Q equals let's see, V1, oh. Okay, Q is 15.708, is this in feet? It's cubic feet per second, equals V1 times pi times D1, which is 2 feet squared divided by 4. Okay, so V1 equals, let's look at my notes here. Oh, look at that. If we keep 5 significant digits, we get this. Oh, except we actually get feet per second. Okay, don't make that mistake. Feet per second. Okay, so that's useful. Okay, and we'll do the same thing and say 15.708 CFS equals V2 times pi times 1 foot squared, that's a pi, over 4. So V2 equals 20.000 feet per second. Seems contrived. It might be because I made that number up. All right, anyway, so now we got V1 and V2, so that's good. Now we could solve this problem mostly, but we would still need, I wish I could just kind of like separate that so it won't be in the way. Okay, so now we still need P1 and P2. Okay, so continuity, we've used it. Let's try the Bernoulli. Okay, let's see if Bernoulli will be helpful. P1 over gamma plus Z1 plus V1 squared on 2G equals P2 on gamma plus Z2 plus V2 squared on 2G. All right, so let's see if this is going to help. We're trying to get at P2. Z1 and Z2, we need our points. So here's point 1, and here is point 2. Okay, so the pressure at 1, is it given? I think it was given. Yes, the pressure at 1 is given. 21 PSI. Oh, we hate PSI. Okay, so we're going to use PSF. Right, and to get PSF, we need to start with our 21, what was given? 21 PSI, so that's pounds per inch squared. And we're going to multiply that by 144 inches squared per 1 foot squared. Okay, so that's going to go on top of gamma. Gamma in this case, this is water we're talking about, so the gamma of water is going to be 62.4 pounds per cubic foot. So notice we've got cubic feet on the bottom down here, or pounds over cubic feet on the bottom, and we've got pounds over square feet on the top. So that's going to leave us with, this is going to come out in terms of feet, which is what we want. Okay, now Z1 and Z2, so this is where we, so the next thing we got to deal with is Z1. Z1 right here and Z2, the only thing we know about them is that Z2 is higher than Z1 by 2 feet. 2 feet. Okay, let's undo that. But anyway, that distance is 2 feet. So we can know that, so knowing that helps us because it means that Z1 can be 0, and that's going to make Z2 2 feet. So when we get to Z2, we're going to make this 2 feet. And that's coming from geometry. So we are going to use a little geometry here. And we're using Bernoulli. Okay, so now V1 over 2G. We know V1, it's 5 feet per second. We solved for that a second ago. We're going to square that, and we're going to put that over 2 times 32.2 feet per second squared. Okay, so that's the right-hand side of this equation. The left-hand side of this equation, looks like I'm going to have to bleed over onto the other side here. Hopefully that won't create a problem. I guess we're going to find out. Okay, so over here, P2 is what we're looking for with all this, because that's going to help us solve this problem, 62.4 pounds per cubic foot. Okay, on the bottom. I apologize for that shift there. Okay, plus, now Z2 is 2 feet. So again, at the beginning I kind of mentioned, we can kind of try to figure out whether or not that 2 foot rise actually matters. And we're kind of getting at to where that would matter, because we're putting it into the Bernoulli equation, and we're going to be able to compare it to the other terms to see if it's really important or not. Okay, so then we've got V2 over 2G, and V2 is, what is V2? Oh, 20, I believe, yes, 20 feet per second squared. And we're going to put that over 2 times 32.2 feet per second squared. Okay, notice the difference between feet per second squared and feet per second squared. Okay, so if we solve this, I could just write P2 equals, but I'm actually not going to do that. I'm going to kind of show these terms here. 48.462 feet, okay, plus, well, obviously 0 feet, plus 0.38, excuse me, 8. Ugh, horrible. 38820 feet equals, well, P2 over 62.4 PCF, plus 2 feet plus 6.2111 feet. Okay, so a few things to note. There's a few points of interest here. First of all, this 0 to 2 feet right here is not terribly important when you consider the magnitude of these other terms. Okay, so it's probably a fair assumption if you wanted to just, like if you were in a problem and that it was not given, you could assume this was 0 if you wanted to. Yeah, it's going to make your life easier. It's obviously going to be more exact if you actually know, what that distance is, what that vertical distance is. But it's okay if you didn't do that. Okay, so and we won't in this case because we have it. The other thing to note is that so see where pipe 1 is. Okay, so it's right here. Okay, and we want to notice a few things about this. First of all, this pipe, our expectation, okay, for Bernoulli basically says that this quantity here is going to be the same anywhere along a streamline if we assume incompressible flow and that it's inviscid and all those other things. So one thing that we should expect from this is that in this case, as we go from 1 to 2, we're trying to drive at what the pressure is here. Okay, but we notice that the Z value increased. Okay, the Z's increased going from 1 to 2, and the velocity also increased from going from 1 to 2. Okay, and the velocity increased because the pipe got narrower. The pipe went from 2 foot diameter to 1 foot diameter. So because both the Z term, this one increased and this one increased, the only way that can happen for the two sides to remain equal is for the pressure to go down. So expectation here should be that the pressure decreased. Okay, and if we solve for this, we will find that in fact the pressure did decrease. Okay, so if I solve for this, the pressure in fact is 2535.9 PSF. Okay, which kind of like wait, but we were given, you never told us what this number is. Okay, so that's P1. So P1 turns out was 3024 PSF. Okay, it was just kind of given to you in PSI. Okay, so notice that the pressure did in fact increase. Okay, and notice that the other thing to notice from this is that this velocity head, okay, when the pipe got narrower, okay, the velocity head increased, and it went up by a ton, right? Okay, because the velocity went up by a factor of 4, and then we squared it, so this is 16 times as large as this. Okay, so that's a lot of scribble on the side. That's just kind of it should be kind of helpful from an intuition standpoint. As you guys are probably learning, I really like the intuition aspect of these things. Okay, so once we have all of that, we can solve this problem, and it kind of becomes a plug and chug. Now it's going to be a long plug and chug because there's a lot of numbers that have to be plugged in there, but we're up to it. We can do it. Okay, so let's zoom in a little bit so that I'm not writing like Godzilla writing or something. Okay, so there we go. I've got all this worked out so that we're going to have to do it again. So F bow X. So force of the bend on the water in the X direction, And now we're going to go to green. Okay. Plus P1. Oh, that's unbelievable. Plus P1. That's also unbelievable. Okay, we're putting in numbers now. Okay, 3024, 3024. Oh, man. Okay, pounds per square foot, PSF, which means that this area needs to be in square feet. So this is going to be 2 feet squared over 4. Okay, minus P2, which is going to be whatever we just solved for. 25, 39, 35. 5.9 PSF times pi times the diameter, which is 1 foot squared on 4. Okay, cosine 45 plus, now we're going to go into the red because we're getting into our momentum fluxes. This is going to be density of water, which 1.94, you guys should be learning that number by now, slugs per cubic feet. Okay, times 15.708 CFS. Okay, times a positive 5 feet per second equals. Okay, I'm just going to put it right underneath it for the other side of this equation, 1.94 slugs per cubic foot. I wish there was an easier way to write that out. Okay, 15.708 CFS. Okay, 20 feet per second. Okay, times cosine 45. Okay. And if we put all that together, well, I'll just go ahead and solve it over here. Let's go back to our blue. We can go ahead and say that F bow X equals negative 78 13.3 pounds. Okay, again, remember I'm keeping 5 significant digits. Okay, so now we're going to go back and do the same thing for the y. At this point, it's trivial. Some of you guys may, may fast forward through this. There's no way for me to know. Okay, so F Bowie minus the weight, which in this case is going to be the gamma of water, 62.4 PCF. So we need a volume in cubic feet, 10 feet cubed. Okay, that's given. Okay, let's get some green going. Green. Okay, minus P2, which is going to be 35.9 PSF. So we need to multiply that by square feet. So pounds, or pi times 1 foot squared over 4 times the sine of 45 degrees. Okay, and then let's go ahead and get equals. And then we'll do the momentum flux in red. So it'll be 1.94 slugs per cubic feet. Okay, times Q, which is that really ugly 15.708 CFS. And then times positive 20.0, well, we don't need all those zeros, feet per second times the sine of 45. Okay, I apologize for the handwriting there. And then we'll get our blue out here and we'll say F Bowie, F Bowie. Okay, if we solve that, it equals 2463.3 pounds. Okay, so we're going to combine those two now. because we want to know what f is. Okay, so we're going to say f is the square root of f bow x squared plus f bow e squared. Okay, and I'm not going to bother inserting these in here. I'll let you guys do that. F is 2463.3 pounds. Okay, and then theta equals the inverse tangent of f bow e over f bow x. Okay, so theta equals 17.499 degrees. Okay. Wait, something's wrong here. Oh, yes, something is wrong. My apologies. Where's the eraser? Okay, let's erase this number here. Okay, that did seem a little small. Should be 8192.4 pounds. So, so now we can kind of combine those, and we notice that, so actually this should be F bow. So F bow equals, so that's the force of the bend on the water, okay, equals 8192.4 pounds at, stop that, at theta equals 17.499 degrees. This is, let's see, so x direction is negative, y direction is positive. So the bend is pushing on the water in that direction, as we kind of imagined. So here's our theta. So we could say it's 17.499 north of east. Okay, but that's not what we're looking for. We're looking for force water on bend. I believe that was the initial question. If we go all the way back up here, find the force of the water on the bend. If we look right here, so it's going to be the opposite. So it's going to equal, and now I'm going to finally break down to 3 significant digits, 8190 pounds at theta equals 17.5 degrees. And this will be, oh, well, this is a mistake anyway. This was south, north of west, and this is going to be south of east. Okay. So the water, in effect, is pushing that bend down and to the right. So it's pushing it this way. Okay. So if you were trying to hold this bend as it, as it looked like that, you would have to put a force on it that way in order to keep it from flying off, which is pretty cool. Okay, so that's the second problem. And we are now getting close to running out of time. Luckily, the third problem is much shorter. Well, and of course, I accidentally draw things all over the place. Okay, and this one's a little bit different. The other two are pretty standard momentum problems that show up all the time. A dredger loads sand. Let me find my notes on this one. This one's much quicker. A dredger loads sand, which has a specific weight of 2.65, onto a barge. The sand behaves like a liquid. Sometimes it does, sometimes it doesn't. Leaving the dredger at 5 feet per second at 800 pounds per second. Find the tension in the mooring line. Okay, so I think that you guys can imagine this situation. So the sand is piling up. Let's make it yellow. The sand is piling up over here. Okay, and I think you can see that the net effect here of that sand coming out there is it's going to want to push the barge out. And the barge, on the other hand, it's not going out because it's moored right here. Okay, I mean, I live right by the river. I don't see really dredgers all the time, but I see these barges lined up, and they're moored up exactly like this. I'm assuming these sorts of things happen all the time. So, so what we're dealing with here, again, we're gonna do momentum, and in fact, let me steal my momentum equation, which looks all ugly now that I've managed to draw all over it. No, not all of that. Come on, get out of here. Okay, there you go. Okay, let's steal my momentum equation, okay? Because, again, we've got moving liquids and we're looking for a force, okay? So we know we're going to need the momentum equation, which means we're going to need a free body diagram. And so what I'm going to suggest here for the control volume, we need a free body diagram of the control volume. So what I'm going to suggest is that we draw the control volume like this, okay? And so what that means is that if I draw the free body diagram of this control volume, okay, then I'll draw it in blue again. Then I've got a boat, okay, and let's assume that I've tightened that free body diagram up, and I'm actually kind of just getting the boat and not getting the water. I don't want to have to deal with that. Okay, so we've got this boat, and we've got a line of tension right here because you can see it crosses my boundary right there. So we've got tension right here, and then we've got this is all part of our free body diagram, but then we've got a momentum flux, which I'm just going to call V. Okay, and it's going downwards at 30 degrees. Okay, so we're kind of keeping those color coding, right? And so there's essentially two things here. There's a force and there's a momentum flux. Okay, and nothing's changing in time. Okay, so we don't have to worry about this thing, okay, which we probably won't deal with in this course. And so we just have to, let's work this problem and see if we need any of these other tools. Okay, so let's just kind of do this down here. Oh, well, we've got other forces, by the way. We've got weight and we've got force of buoyancy, but I'm not going to worry about those right now because I'm not really worried about the x direction. This tension is only in the y direction, and that's what we're looking for. So that's what we're looking for. Okay, so some of the forces in the x direction. We only have one force in the x direction. It's negative tension. Cool. Okay, now we've got a momentum flux. So we'll change colors. So we'll go plus. So momentum flux right here. Okay, that's coming in. Okay, so I've got m dot, so that's rho times q. Okay, and now the velocity, which is going to be v. Okay, I define it as v right here. And that's just going to be, but it's, you know, it's coming out at 5 feet per second on an angle. So we only want the x component of that, cosine theta. Okay, because I think you can imagine that the portion of this that's going downwards, that's like shooting downwards, is just causing to increase the buoyant force. Okay, because the buoyant force is basically by going downwards, it's going to cause more of the boat to be driven underwater, which is going to increase the volume displaced, which increase the buoyant force. Okay, so anyway, we can talk more about that some other time. Okay, so that equals 0. Okay, so this is pretty straightforward. So we just need to know what do we know and what don't we know. So let's, actually, this is going to be a little bit less straightforward than I just said. Okay, so tension, this is what we're looking for. Rho, well, it's sand, and it's got a 2.65, so we can solve for that, right? Because we know that. The Q, we don't know the Q, right? And I'm not exactly sure how we're going to get at that. Okay, we know the velocity because it's given. Okay, and we know the cosine because it's given. So the problem, this is just a little tricky because we don't know how to get at Q, but we are given this, 800 pounds per second. And the risk here is to wonder, what is 800 pounds per second? And I think that what a lot of my students are going to want to do is they're going to say, well, you know, what is that? Okay, so it's 800 pounds per second. Is that pounds mass or pounds of weight per second? And the answer is really that it could be either. Okay, but the problem is a pound mass is not something that we can use. Okay, this equation, like this thing right here that we're looking for, that's m dot. Okay, which let me draw it over here. So m dot equals rho q equals mass. So in this case, for this equation to work, that could be slugs per second. Okay, so that is the amount of mass entering the control volume per second. Okay, what we've got here is we've got this, and this could either be pounds mass or pounds force. It's kind of up to you, okay, because in some ways they're kind of equivalent. But what I'm going to suggest to you is that we think about this as the weight. Okay, you can think about it as the mass too. But the reason that I want to think about it as a weight, because that reminds me how to convert it to slugs. Okay, and I say, well, weight equals mass times gravity. Okay, mass here will be in slugs. Gravity, well, is in feet per second squared. Okay, and that'll give me this in pounds. Okay, and that's why we're going to do it this way. So I'm going to do 800 pounds equals the mass in slugs times a gravity of 32.2 feet per second squared. Okay, so our mass is 24.845 slugs. Okay, well, that's the equivalent of 800 pounds mass. Okay, or 800 pounds weight. You know, it depends on how you want to look at it. Okay, again, this is a lamentable unit. We hate it. We hope it goes away, but it's not going to. So, so we're going to plug this. So what I'm saying is, instead of thinking about this as 800 pounds per second, I could think of this as 24.845 slugs per second. Okay, which is much easier because I can plug that directly into this equation right here, and I could say negative t plus 24.845 slugs per second. Okay, I'm going to erase some of this because it's in the way. Eraser, get out of here, punks. Good for nothing. Jerks. Okay, we'll go up here, do this, do that. Okay, V is 5 feet per second. Feet per second. Okay, cosine 30 equals 0, so the tension in the line is, well, 107.58 pounds, and of course, this is where I round to 3 significant digits. Okay, and so that's the answer, 108 pounds. And I drew it in the right direction. Okay, so that was an hour 17, so we're a little longer than I wanted it to be. It's my first try. I apologize for messing handwriting. This was really a trial run, so I might have to do it again. Thanks, y'all. Take it easy.